Here's our logic courses textbook, Logics for Computer Science, Classical and Non-Classical, Springer 2019, and I'm the author. And now we are already in Chapter 9. So Chapter 9 is about Hilbert proof system and complete the theorems for classical predicate logic. And it has a lot of parts. It is really a long chapter. It's not that long, but I will cover some parts in detail and other parts in less details, but with the comments where you have to look and what you have to pay attention, as we did in other chapters. So, and the first part, set 1, is reduction predicate logic to propositional logic. That's how it's the first step of a technique of proving the Henking, really, technique of proving the completeness theorem for predicate logic. So the reduction predicate logic to propositional logic, it means predicate logic does not become propositional, but almost, and I'm going to describe now what it is. So when we know already, we have several approaches to the proof of completeness theorem. We did in Chapter 5 2 propositional proofs, and also we did in Chapter 6 the propositional proof of Gentzen type, constructive proof of Gentzen type formalization. So it was Chapter 5 for Gentzen automated theorem proof in Chapter 6, and I will refer specially to the Hilbert-type proof system in Chapter 5. And then we will do in Chapter 10, we will generalize propositional proof for propositional logic proof to the predicate logic. Is a very beautiful proof and much simpler what I'm going to talk to you about today. So the proof and the method I'm presenting here is in big detail. As you know, I like the details. Is a Henking proof included in a classic Handbook of Mathematical Logic by North Holland Publishing, 1977. Okay, also, and it contains the method of reducing problems of first-order logic. I follow in detail that proof. How much detail is needed to understand published and very recognized proof, that by Chapter 9 is the proof that you need to put a lot of details in order to understand. That proof is about 5 pages, and we have 50 pages, so 300 slides. So that's why also I'm talking about it to explain to you that often when you read in a textbook or you read in a paper, when you read a proof and you have hard time understanding, it is because a lot of details are missing, and my goal is, as you know from the beginning of our course, my goal is to fill in all the gaps so you can understand. And also, if you understand how one fills the gap, you will be able to do it by yourself once it is needed. So, steps. Here are the steps. Reduction to propositional logic theorem, compactness theorem for the first logic, Löwenheis-Collin theorem, and Gödel completeness theorem. Gödel completeness theorem of predicate logic. So all those proofs of all those theorems, which are basic theorems about very basic, in a sense, the most important theorems in predicate classical logic, they all fall out of the Henking method. So, and we will do it. So, reduction, first step is reduction predicate logic to propositional logic, what it is. So, here we have our, and I'm going to write it down, you have our language, and I will keep it, which we have all connectives, negation, conjunction. So this is our connectives. And then we have full set of, as we said, full set of predicate functional and constant countable, each of one is countably infinite. I already mentioned you, we consider the language with equality. What does it mean? Because that's what we will be doing. I will talk about it again later. But language with equality means that there is in P, it means there is a predicate that which we denote equality between there is a predicate which we denote in P, between our predicates. So this is called the language of equality, and that because it represents equality and we'll have axioms for equality, so I will use that notation in example. So we have a predicate. The only other predicates, as you remember, you write letters for relations, but this we write what we, because intended interpretation would be equality, so this is the only one intended interpretation predicate, two-argument predicate in P. So that is our language, is the language with equality, so don't be surprised if, and I will define that language with axioms and so on later. But that is for our purposes, that's we have this language of equality. And now, in the reduction, we have PF. So now P is for propositional. So this stands for propositional formulas in our predicate language. And we are going to define it. That set of proposition is a subset. PF is a subset of set of all formulas of which we call propositional formulas. Intuitively, propositional formulas are direct propositional combination of simple formulas that are atomic formulas or formulas that begin with quantifier. So, for example, you can have Rxy is atomic formula, and so that would be a propositional formula. You can put quantifier, any quantifier, in front. So this is atomic formula, and then any formula, but any formula. Now you have any formula in L. So when you have any formula in with A, for example, for all x, P x implies there is y r x y, and that is a formula of our language. And now it is a propositional formula if you put any quantifier. You need to put quantifier in front, and here is A in whole language of F. So now, so it means you can, you accept normal formulas from our language if you put a universal quantifier in front, or existential quantifier. So you have universal, or also you can put there is whatever you y, and here you have A. So you need, if you must to accept in the propositional formulas of our language, you must have a normal formula and put the quantifier universal or existential in front. So now you can see nice definition, propositional formulas, and here you have the atomic formulas. First, atomic formulas, we know what is atomic formulas, and or you have any formula of the language which we put in universal quantifier in front, union, because this is a set, or you can have any formula and put existential. And AF is the set of atomic formulas, and prime formulas are such a special subset of the whole set of formulas of our language. And here is some examples. Here is atomic formula, T1 are terms. Here you have AX is any formula of our language, but we have to put quantifier, any quantifier. Here I have C equals C. This is atomic formula because we assume that this is, C is a constant, so this is PCC, where that is a quality, and we write it in our language, C equals C, because we have this intended interpretation of equality. So that's why that is our atomic formula. And then you have another, for example, you have two atomic formulas, implications. So they are called propositional formulas because you have those formulas and you use only propositional connectives. So you have, like, instead of variables, propositional variables, you have those propositional formulas, and you have a propositional part in the sense that you use only propositional connectives. So you have propositional formulas, absolutely the same definition as we had for the propositional formulas of our propositional logic. It means if F and P are set of formulas and P are the prime formulas, so F is the small propositional formulas, is the small sets that propositional formulas are, the prime formulas are propositional formulas, and then you use normal connectives, A, B, A implies B, etc. So, and these are called P, our P are called atomic propositional formulas. Just to remind you, P is that set, right? So I explain you what the P is. And so, and P stands because it's propositional. And now we define, as similar as we did in propositional logic, a definition of a truth assignment. So now truth assignment, if P is atomic propositional formulas. Now, how we had in propositional logic, right? Truth assignment in propositional logic, we have as variables, propositional variables into TF. So now our propositional truth assignment in our first-order logic would be V, which takes variables with atomic formulas. So now you have atomic formulas, and in TF, so you have, instead of variables, those atomic propositional formulas of first-order logic, of predicate logic, replace our variables, and it's called the truth assignment. And now what we do, of course, we extend, as we did in this case, we extend to V star, to all propositional formulas. I want to P propositional formulas, because in predicate language, to TF, here in propositional case, V star, we use the same notation, was propositional formulas into TF extension. So, and now our formulas are propositional formulas in predicate logic, and we do exactly the same. V star is exactly the same definition as we had for propositional case extension, right? And these are our connective defined by, in our extensional, by our truth tables for the proper connectives. And we say that, we repeat the same definition, the truth assignment is a model if evaluates a formula into T, and for any formula, we say that a formula, propositional formula in predicate logic, so remember PF is propositional formula in predicate logic, is a tautology if and only if V8A is T for also all V are models. I am repeating all the time propositional in predicate logic, etc., propositional model in predicate logic. So for sake of simplicity, we will say now model tautology instead of propositional model, propositional word within the predicate logic, so you know what's happening. No, now we say that propositional formula, for any propositional formulas in predicate logic, we say that V is the propositional model of the set of formulas, again the same definition as we had in real propositional case. V is a model for all formulas, and we have definition of consistent set, which we'll be using a lot, that the set of formulas, propositional formulas, is consistent if it has a model. It means a propositional model, and inconsistent set is inconsistent which does not have a propositional model. And now we have a compactness theorem for propositional logic of L, of that L. The set S of propositional formulas is consistent if and only if what every final subset is consistent. We already did prove it for real propositional logic in chapter 5. So in proof 2 of completeness theorem in chapter 5, and I will be referring to it pretty often. So, for example, assume that S is consistent set. By definition, it has a model. Its model is also model of all subset, included finite subset. Hence, all finite subset have a model, so that is one side is very obvious. To prove converse implication is non-trivial. And half of the compactness theorem, we write it in slightly modified form. It means we have a definition. Any set S such that its finite subset are consistent is finitely consistent. So I will write it this because we will, that is one of important definition. S is finitely consistent. S means all finite subsets of S are consistent. So now we will be talking about finitely consistent sets. So compactness theorem is which I'm going to prove. This theorem is S of propositional, let's write it like that, S subset of propositional formulas, it has to be P, for propositional formulas of L is consistent if and only if is finitely consistent. So this is, it means, okay, the names of consistency, of compactness, because the compactness says set is consistent if and only if all finite subsets are consistent, comes from topology. And in topology, this theorem between that relationship between a set and a finite sets is called compactness theorem. Similar, not that, but similar the property. Relationship between a set and its all finite subsets is called compactness theorem. So we use that word from topology. And of course, the non-trivial find have to be proved. So it means we have to, now it's stated every finite consistent set of propositional formulas is consistent. This is our compactness theorem, and the proof has 4 steps. We introduce the notion of maximal finitely consistent set. We show that every maximal is the word, finitely consistent set is consistent. We do it by constructing a model. We show that every finitely consistent set can be extended to maximal. And you see, we put a star because we have this extension. It's like V and V star. Extension to V was V star, so extension is a star. And we show that every finitely consistent set, there is a set S star such that that is extension and S is maximal finitely. And so, and then we use those steps 2 and 3 to justify the following reasoning. Given an finitely consistent set S, we extend it by construction, and I will show you the construction, to S star. By 2, the set S is consistent, so is the set S star is consistent, so is a set, its subset. So this ends of the proof of compactness theorem. So when you look at those steps, and even at notation, and go to chapter 5, proof 2 of completeness theorem, all the definitions are the same, but the set S is called delta. So when I am not going, and that proof too has more details, exactly each single detail than the proof I'm going to show you today, but it's exactly the same proof, and that I deliver here my promise, which I gave you in chapter 5, that this is this horrible long proof of completeness theorem of propositional logic. We will use it. It's exactly the same technique we'll use in predicate logic, and here we are using it. So it's a good moment, if you don't understand something here, go to chapter 2 and see how we did it in all details. So now, exactly is the same definition. We introduce the definition of maximal finitely consistent set, MFC, which has that property that A, for every formula A is in S or negation. So that maximal finitely consistent set separates a formula and its negation. And it's called maximal filter and so on. So that exactly the same definition which we did in the chapter 5. And now in step 2 consists of proving the lemma. Any maximal finitely consistent set is consistent. And here's the proof. So prove the consistency by constructing a model. It means that we construct a truth assignment that for all A in S star, VA equal T. And we will do it. So this is, we will do it. And we have such a property that for maximal finite consistent set S, for every formula or negation belongs to S. In particular, the atomic formula belongs to S. So we have justified the following definition and our V. So once we have, I didn't construct yet this S star. So, but S star is maximal finitely consistent set. S star to be constructed is maximal finitely consistent set. And now we have a mapping which takes our atomic formula, prime formula, into TF. That was V variables in the TF in chapter 5, such that VP from prime formula is T when P, a formula, belongs to S star, and F if P does not belong to S star. And this is truth assignment defined by that maximal consistent set. Check chapter 5 is exactly the same definition. And we extended this V to the set now to all formulas, and to the truth assignment to show that the truth assignment is a model for S star. It means we want to show that VA is true with A, any formula belongs to S, or F if doesn't, and we prove that by induction on the degree of the formula A, exactly the same as we did in chapter 5. And I really copied that proof from chapter 5, so you can read one or the other. Instead of delta star, or delta is S and S star, so that is exactly the proof. We already did, and we do it by induction over the degree of the formula. So if A is B of C, you go and you do the induction, and you prove that that lemma holds. And now the next step, so adds the proof of the lemma and completes the proof of the step S2. Now, maximal finitely consistent set is an extension of S. So that is also we have to prove. We assume that we have it, and I haven't constructed yet. So, and we construct the extension S prime, extension S prime of S as follows. Again, exactly the same way we did in chapter 5. The set of all formulas is infinitely countable. So now the set is PF. We put it in 1-1 sequence. And now for this 1-1 sequence of the PF proposition of formulas, we define a chain from S0, S1 of the sets, where the first set is our S, and we extend this S. This is our S. We extend it to our S star. So we construct this chain of extensions that S0 is S. And remember, maximal S was that A belongs to S or not A belongs to S. So that was the property of S being maximal. So Sn plus 1 is Sn plus Sn if An is An. Sn is infinitely consistent, is finitely consistent, or negation otherwise. Exactly the same definition as we did before. And again, S star is the union of all those sets, and obviously is maximally finitely consistent because every formula is in S star or negation by the construction. And now to complete the proof that S star is maximal finitely consistent, we have to show that it's finitely consistent. So again, proof is the same as we did before. So we observe that if all sets are finitely consistent, so the union is also finitely consistent, because namely, let's SF be a finite subset of S star. It means that all those sets are in our chain constructing, and we have Sm, you have maximum of all I k, so SF is in Sm, and M for M equal maximum, you take the biggest one because they are all finitely consistent. And so it means Sm is finitely consistent as an element of our chain. So it proves that all Sn are finitely consistent. So again, exactly the same proof as we did in chapter 5. And also, now we have to prove only that all sets An are finitely consistent, and we do it by induction over the legs of our chain, this chain, which we constructed like that. And here's the proof. Remember that Sn is Sn added An, or you have Sn plus 1 is, then Sn is finitely consistent by definition of the chain, and then you have Sn plus 1 is a union negation, and you consider this case. I'm exactly the same proof as we did in chapter 5. So it's nice to have those two proofs that you can compare them, and we already did it. So that completes the proof S3. So we complete the proof of compactness theorem by the following argument. Given a finitely consistent S, we extend it via our constructions, which we show, to maximal finitely consistent. This, you see, the whole construction you have finitely to maximal because we need those separation of A and not A, because when you go back and you look of our definition of truth assignment, you see T and F at A in S, and then you have A does not in S, it means negation by maximality, negation is. So you have that separation of A and negation of A. So now we have that, we extend to maximal by S2, S is consistent, so is the set, so that ends the proof of compactness theorem. Now, we are getting closer. So that was the proof of compactness theorem. Now, our goal is to prove, to define a method which is called a Henking method, and to prove now we know the reduction to propositional logic theorem, which I'm going to formulate, what it really is, what this reduction gives us. And now we prove the compactness theorem for the predicate logic and call them Lovenheim theorem. So propositional tautologies in L barely scratch the surface of all tautologies. For example, these are nice propositional tautologies because this is A or not A, and so on. But, for example, such predicate tautologies are not propositional tautologies because in our propositional tautologies, that would be just a formula, and I cannot get inside it. Propositional tautologies rely on the connectives only, and here it relies on the quantifier. So we have to sort of put together the relationship between propositional tautologies and the whole tautologies, and to prove completeness, we need the notion of. We use the notion of tautology of the full language, so we have to do a little bit more work. Also, there is a language that we use the word valid formula in literature for predicate tautologies, just not to repeat all the time propositional tautology, predicate tautology. For predicate tautology, we often use the word valid formula. But we will keep using predicate and propositional tautology. So now I remind you basic definition. What is predicate tautology? So given our language and with the set of variables of the predicate language, a structure, you have a structure for the language with the universe M and interpretation. S is an assignment of variables of the language into the structure, and then you have A is satisfy a formula of the whole normal big language. A formula is satisfied by the structure. If there is a variable assignment such that MS, the structure, and that assignment satisfies A, and it means A is true in M. And A is true, we say that M is true in that structure M. We say that if MS satisfy A for all truth assignments. So we already covered the definition, and the structure M is a model. In this case, if M satisfies L, or A is true in the structure, this is called a model, and predicate tautology, or A is valid. is a predicate tautology valid if it's true in all possible structures, right? So that was our definition of tautology, and we will use tautology in this chapter, just tautology A without putting little p here. And in the case, remember that in a case which we also proved, that A is a sentence, it means if a sentence, the truth and falsity does not depend on S. So we write that M is a model if for some S, MS is model, and the same F is model for set of formulas. So this is just a reminder of basic definition. And now, I say that we have to see which are the difference between propositional, real propositional models and propositional models within predicate language and models in predicate language. So predicate models are defined in terms of MI and assignment, right? So these are predicate models. So predicate models is ME structure S, and this we called M just to have less, and we say that, okay, S, and we say that, and you have S is variable assignment in predicate language in now universe of the structure. So models are defined in terms of structure and assignment of variables in the structure, right? So this is relationship between a structure and formulas. And propositional models is now in our L, of course, F are prime formulas into TF, right? So that's why it's called propositional model, because, and we define this V and extension and so on. So the relationship between predicate and propositional models we can write as a lemma, given a structure for the language and variable assignment. There is a truth assignment in this sense, such that for all formulas of the big language, MS, see, so I have M structure. So this structure MS is model of A if and only if V star A equal T. Or you can say that V star, that propositional V is a model of A. So here you have a structure, and assignment, and here you have our V, that's why it's called propositional model. And of course, in particular, for any set S of sentences of L, no free variables, if M is a model of S, then S is consistent also in propositional sense. And here's the proof, right? For any prime formula, VA, you put VA T if now MS satisfies A, F otherwise. Since every formula is A the prime or built from prime formulas by means of propositional connectives, the conclusion is obvious. And this is important implication of the lemma, that if M is a model of S, so this is a predicate satisfaction, then S is consistent in propositional sense is far from true. So that goes only in one direction, and there is an example that doesn't hold. So now we set it up all our propositional models and remind you the connection between the full predicate models and connection between full predicate models of the formulas and propositional models. So now we have we are ready to define our proof system slowly. So language. And I promise you that I said that we call the first order language a language with equality if, I erased it, if between the predicates you have equality sign and we use it as intended interpretation, and the language is with, so it means that language is with equality and we have equality axioms. And these are obvious axioms how we understand equality. So now all this U, W, they are all variable or constants. And this is normal equality, and that is if R is an argument predicate, if all arguments are equal, the R holds between those arguments, that R holds between the other arguments. So these are obvious axioms which of equality. And you can see that for given structure, we have by simple verification for all S and for all formula which are axioms, these are MS are models for A, so equality axioms are predicate tautologies of L. So that's why we call logic with equality, we call now logic with equality axioms, added to it just a logic. So, so we always can have in tautology, because the completeness theorem for the logic is tautology if and only if has a proof. So now we just call it a logic, and we can have all those axioms in equality, and we will be using them in the proof. So that's we have. Now, the next important notion is called Henking witnessing expansion. So now we want the technique, Henking inventing a technique of reducing predicate logic to propositional logic, like the whole. And we use that techniques because we want to have those propositional models and so on. So we construct expansion of the language. We have our language, and now we add, which is called a Henking expansion of the language, by adding new constants to it. And we build a new set of constant, thin C, which is disjoint with the old set of constants. So we add expansion, means we have this whole language, we keep this, and we add new constants. And this, such constructing language with those new constants is called witnessing expansion of the language. And this is our language. And LC, these are new constants which are called added to old constants, which are called witnessing expansion. And how you do it, we have a construction. The idea is we define the set by constructing, by induction, infinite set of constants together with extension languages. We start for empty, and L0 would be L and L0. And now I'm going to explain how you construct those constants, what they mean. Notation, A with, okay, that is important because we will use this notation a lot. Now, we have, remember, we have A. X means X appears in A. So that A has X between other free variable as free variable, because, right? Now we write A in square brackets. A has exactly one free variable. So here A can have many variables, and here exactly one free variables, free X. So that I will keep it. All right. And this is the key. And for each formula, and we introduce a constant defined by that formula. We define a constant for each formula, a constant defined by that formula. How? Okay, the idea is that okay, in general, we define that C1 is you define this constant. And then you do it by induction. What is this constant? And then you have as C the whole union of all these constants by witnessing expansion you defined. Now, what is this constant really? That constant is the name. If you have universal quantifier, if you have, there is XAX, is true in a structure, we choose an element satisfying this AX, because there is, and give it a new name, which we called constant for that formula. So really those constants, if you have, there is XAX, those constants are names of those x's which exist. So we, for each universal quantifier, you said, oh, here is my name, and we add all the names for those x's for which that formula is true. To do so, we have what's called Hecking axioms. There is x, ax, this x becomes the constant, and if I have A where of constant is a constant for the negation of x, you have for all x, so that's the Morgan law. And so it means that the idea is, for there is x is true in the structure, we choose an element satisfy, and you give the name. And that is your constant we add to the structure. And this is, if it's false, we choose the counterexample. That you choose the counterexample and call it a new name. It means a constant to negation of AX. And we have another sentences that another axiom, quantifiers axioms, for all XAX is AT, where T is closed term added to those constants, because each time you add those constants, NAT implies there is XAX. So the T is a closed term, is called quantifier axioms. And of course, you can check that obviously the predicate tautologies. And now the Henking set is there's any set of sentences, LC, of this unrich language is A, the Henking axiom, or quantifier axiom is called the Henking set of the Henking set, if we write as Henking. And the sentence is obviously not true in every LC structure, but we are going to show that every L structure can be transformed into LC, L structure for the whole language, for extended, which is a model for those Henking. This extending, you see, because those extending for each, there is XAX, you add the name of that X which satisfies there is XAX. And then you go new reduct, and we have M is a structure, and L is witnessing expansion. You define the witnessing expansion, and then you show that witnessing expansion is a model for the set of Henking set, any Henking set, and then which means that to define interpretation on any C of those new constant, we define in a proper way. I'm not going to go into, and everything is nicely, like for example, lemma holds for Henking axiom, must hold for H2, and you work it out that everything is as it's supposed to be, and that is a Henking. That is a Henking construction, right? And then we know, and we prove the lemma. We define C is the union of all CNs, and you do it by a mathematical induction, step by step. Inductive step, there is no one step missing. So, and that all needs to definition of what is called canonical structure. So given a structure normal for the language, an expansion to the larger language, adding all those constants, and M is called a canonical structure for expanded language if all A in M are denoted by some C in the new constant. So M is the notation of C for the C in new constant. And you have a reduction theorem that if you have predicate language and you have the witnessing expansion, which we defined, and for any set of sentences of L, we have S has a model. It means a model for the language, the full language L, such that M is a model of A for all A in S. It's model of S. So that is equivalent that there is a canonical structure for extension, which is a model for S. It means such that M is a model of A for all A, and this is logically equivalent to that the set S Henking inequality is consistent in a sense of propositional logic, where EQ is the set of equality axioms. So that is the reduction theorem. It means that you have you have the canonical structure, and a model is equivalent to a canonical structure model, but this is equivalent that to the fact that S Henking axioms inequality is consistent in the sense of propositional logic. So this is reduction theorem. And then we prove nicely, you see, VA equal T. We have to prove that. And we go step by step, you need the closed terms, you have all the technical definitions. So And we define universe, we define our M, we specify universe, we specify interpretation of terms, and now for constant symbol, that is normal, C, you have interpretation of those new C as follows, that Cm, M is a model of A if and only if that is connection with the our propositional model, holds for all sentences in our extended language, witnessing language C. And now we have to define this canonical structure. So definition of the universe of canonical structure is, first, we define equivalence relation on a constant of the added constant. So we say that two added constants are equivalent if V, our propositional V, this is our prime formula, is true. And the equality axioms guarantee that this relation is equivalence relation. That's why we have logic with equality. And then I prove you reflexivity, symmetry, nice exercise on equivalence relations and using the definitions and transitivity, very nice definition. And we denote by bracket C equivalence class of C, and our canonical model universe are equivalences classes of those witnesses constants which we added to our original constants. So these are, so you can see the universe of the model are those not only C's, these new constants, which denoted really the elements which existed in metaphysical sense, but also equivalence classes. So it's, if you have an element which exists, but maybe more than one, so they are equivalent if they are the same in a V of C equal D equal T, so they are true. And now you have, so this is universe, all those equivalence classes of those new constants. And of course, R would be obviously that R elements C1, Cn, those from universe hold if our V, our truth assignment, this is our prime formula, because it's atomic formula, V of this is T. So, and of course we prove that it's well defined, and this is what nice proof that that relation is well defined. Nice proof. As I promise you, there's no one little fact missing. Very nice, and it shows also how you use the equality axioms, how important role they play, and so on. And now functions, we say that if you have the constants, we claim that there is C such that f of those constants is C if the value of f equals C. So you see, this is a term which is equal C, so this is a relation. So you have this, this is a prime formula, atomic formula, the value is T. And then I show that it is all true, again, in all nice details, which step by step is very useful to see. So, and then you say that because we show that, we define that interpretation, this is F is an argument function of our universe, but elements of our canonical universe are equivalence classes, is equivalence classes such that V of real term on those constants is that C is T. And then you also prove that is well defined. And of course, our interpretation of a constant is that equivalence class and that belongs to the universe of the structure. So, and then this is a construction of, this is called a canonical structure of M. And we prove a property that for any formula, M, the canonical structure is a model if and only if VA equal T. So that holds for atomic propositional sentences, and we have to show that it holds for any B in P. And then again, you have a nice proof by mathematical induction and definition of satisfaction, step by step. Here is, when you have a sentence, there is XAX, we have to show that M is a model if and only if V star of that is T. So, and then we show that it's really true. And also, yeah, so you go step by step, and wait, sorry. So what is important, that reduction theorem gives us a method of constructing models out of symbols of canonical models. And Henking was really, it was back together. I'm going to give you history a little bit. So this is a modern version of Henking proof, which was much more incomprehensible, much more difficult, but Henking proof was improvement on Gödel original model. But importance is that this is the first construction of a model of a language out of canonical model, out of symbols, that the set of symbols can be model of a language. And also that gives the proof of two important theorems, compactness theorem for predicate logic and Löwenherz-Kolem theorem. So now compactness theorem for predicate logic says if now you have the whole formulas, right? We did compactness for those propositional pieces. Now it says that for full formulas, our full-fledged predicate language, for any set, you has a model if and only if any finite subset has a model. And assume that set is predicate formulas such that as any subset has a model, we show that S is a model. So this is in this implication. And here it's it uses the reduction theorem, which says if S0 has a model, that the set S0 plus Henking plus equality is consistent, it means has a model. So you can see we use here the compactness theorem from propositional logic. So because we have it, it's sufficient to prove that every finite subset of this has a model. So that's how we use compactness for propositional logic, for compactness for the whole predicate logic. And I just wanted to show you, because it is how quickly you get more sophisticated. Löwenherz-Kolem theorem is about, you know, here the model was a canonical structure. So there were equivalence classes of this countably infinite constant added to our language by witnessing expansion. So the cardinality of that model, it means there were countably infinitely many elements in that canonical structure. So it is countably infinitely many model. So it means that if you have a language, it has model which structure is countably infinitely or of cardinality Aleph 0, the same as natural numbers. So now, of course, mathematicians immediately jump on it and say, let's K be any infinite cardinal. So we are out of, not only because we consider only languages of cardinality Aleph 0, it means countably infinite. In our structure till now, in our whole consideration, we dealt only with countably infinite alphabet, countably infinite formulas, countably infinite. So countably infinite is cardinality Aleph 0. So you have cardinality, countably is Aleph 0. So this is a cardinal number which expresses countably infinite set. So now you have many other cardinal numbers. So let's K be any infinite cardinal, L be a predicate language with alphabet which has less equal. So you can have alphabet as many as real numbers, or subset of real numbers, and you have the whole universe of infinite cardinals. Now, let gamma be a set of K formulas. It means from that set, and if set has a model, there is a model S such that the cardinality is less equal. That here, the model, the canonical model, had the cardinality of M was less equal Aleph 0. It was really Aleph 0. So in general, all the models which we were getting were cardinality at most infinitely countable or finite and so on. So now you have the generalization for any infinite cardinal, and that is a beautiful proof. You have reduction theorem, you repeat everything what we did for Aleph 0. It means what we did for countably infinite languages, we repeated it. And now we have a completeness theorem, and now I just want to a history. I already said a little bit of this history, but let's repeat it because it's important. Gödel completeness theorem for predicate logic. He did it in 1929 in doctoral dissertation. So that was before he proved those Gödel incompleteness theorems, which we'll study in chapter 11. So his incompleteness theorem, he was 22. So here, I don't know, he was not 20 yet. And published in 1930. It is really impossible to read for us. But, and also, he invented it all. So the language which I'm teaching you, the language we use in 21st century, is a pretty well-established and comprehensible language if you sort of start from the alphabet and learn all possible words of that alphabet, but it's very precise and comprehensible language. But at that time, things were not yet, the proper language uniform wasn't developed, but the ideas were there. So the Gödel proof was simplified 17 years later by Henking. That's why we took the Henking method. That's why we did the whole Henking stuff. And in his PhD thesis, that he really simplified and explained in a more formal way the model existence theorem, those canonical structure, and was published 49. And then Henking proof was much more complicated than I show you, which was published not long ago, and was simplified in 53 by Hassenjagger, Gisbert, I hope I pronounced properly, Hassenjagger in 53. So what we get, the Henking proof, it's modern proof, which is really very, very simple comparing to the long time we got to the stage we have presented you. But also, there's not only those proofs. I choose to show you the Henking proof because this is the most classical. Like you take logic book, Mendelssohn, the Henking proof is there, and you should know of existence. Now, you take these techniques and you generalize them, simplifies them. That's how the research is being done. So, and I will use Rasiowa-Sikorski, 51, 52, use algebraic method invented by Bethe, by Tarski and Mostowski and so on, and that led to algebraic methods, algebraic models, which we covered in chapter 7 for modal logic and algebraic models for classical logic. Beautiful proofs, really much easier to understand, but it wouldn't happen if not for the previous work. And Bethe in 53 used topological method. That's totally another language with topology. And then other proofs is in Hintikov, also very famous, and Bethe in 59, and also what we I want to mention that in chapter 10 soon I show you the Rasiowa-Sikorski automated theorem proving QRS for predicate logic, which with the shortest and the most comprehensible proof of completeness theorem. Similar, remember the proof for propositional logic with the tree and construction of contramodel on the tree, which was so easy. The Rasiowa-Sikorski proof for QRS system is like that. So you can fully appreciate if you went through the through today's lecture. So now I will just show you that Hilbert proof system, and I will show you how the sketch how he proved the completeness theorem. So logical axioms, propositional axioms, equality axioms, and quantifiers. So logical axioms is PA, is propositional, equality, and quantifier axioms. So in some, like for example, in some handbook, they just even don't state those axioms, propositional axioms. They said, oh, we take all propositional tautologies. Of course, so it means that you can take any propositional axiom system, which is already propositionally complete, so you have all the propositional tautologies and so on. But we just state them. And equality axiom, which is the same as before, we use in the proof of reduction to propositional logic theorem. And the set of quantifiers is the Henking set of quantifiers. So we have all, and you have modus ponens, rule of inference, and then you have quantifier rules, G1, G2, generalization rules, and we have modus ponens, generalization rules, and all these axioms. And here's the set of axioms. It's nice to see them. So this is Hilbert 1928 set of axioms, 15. A or not A is the last axiom. Equality, we already have it. You have quantifiers axioms, two quantifier axioms. And remember, this is substitution, free for x, and so on. We went through it all. So, of course, it comes with needed assumption. You have modus ponens, and you have generalization for A. You can deduce for all xa. And in particular, this we write if x has A has an x, so you can bind the x. Here said that you can bind by any variable, but you really use that form. And generalization, very important rule, G1 and 2. There are two generalization rules. And you can see how then you have formal proof, as we had. You have formal proof from hypothesis, as we had before. And we write Hilbert proof A. A has a proof in this. So in particular, if gamma is empty, you have that. And you have completeness. And because we've affixed the proof system, we just write without which system. And now you have to prove the completeness theorem, soundness theorem. We write as normal, and soundness proof pretty easily as usual. And now our goal is to prove completeness theorem. A is probable in our system H if and only if is predicate tautology. It means valid, which we write proof. And tautology, now we are in predicate language, so that means predicate tautology. And we prove by using Henking method for 47 in a more modern and better version. So we need certain important notation. It means we want to have sentences. We'll be talking about sentences. So sentence, if you have a formula with variables, you use universal quantifier, and that is called, you bind all the variables, and you have a closure fact. The formula is a tautology. You can, the closed formula, the closure is also a tautology. And logical implication, you have logically imply if M is, if F, that is called F gamma. You see, we had the proof from gamma. And now you introduce the notion logical. You say that gamma logically implies that if all models of gamma are models of A, so if it means that to prove that gamma is B logically implies, follows from set of formulas gamma if all models of gamma are models of A. And now you can write the lemma that for any set of sentences, gamma proves a formula if and only if gamma proves the closure of that formula. That's trivial by axioms. So if a formula is tautology, so is its closure. If a formula is probable from gamma, so its closure is also probable. And now we formulate the Gödel completeness theorem in terms of probability from gamma, and that gamma logically follows from gamma. So a sentence is probable if and only if the set gamma logically implies A, and that's how Gödel did it. And then we want to remind you that reduction to propositional logic is integral part of the first part of the proof of Gödel completeness theorem. And we here, you do it in, we do it separately because it's just easier, let's put it like that. And I explain why. And now I bring back the definition of consistency, right? The set of formulas consistent if it only has a model. So you have inconsistency lemma that if gamma logically implies A, then the set gamma union not A is inconsistent. You see, we already had those extensions. So we can remodel everything into what we already said in terms of gamma. So we prove that if gamma proves A implies B, and gamma proves not A and B, that gamma proves A, and you have different properties. So that is a crucial lemma, which all these properties we'll use later in the proof of completeness theorem, and I prove you step by step. It's a very nice, yeah, it's a nice exercise. So how you apply the generalization rule, etc. So everything is beautiful, and here's the end of the lemma. And now our H completeness theorem, which we are going to prove. So this is our system. Gamma proves A if and only if gamma logically applies A. In particular, for any formula, when gamma is empty, you have our simpler, our like standard completeness theorem. So now I just want you to show completeness part, and that is, you know, the one part is soundness, which is trivial, we've done it. Completeness part is if gamma logically implies A, then gamma has a proof. So it means, that means before was if gamma is empty, so if gamma is tautology, from that information we deduce that A has a proof. And remember, our proof of completeness theorem in chapter 5 was, first proof was like that. We had the information that formula was a tautology. It means for all truth assignment was true. I show you how that information constructs a proof. So open chapter 5, proof 1, and this is a sophisticated version, of course, because adopted to this rich predicate language of that method of proof. So this is like forward proof, not by proof by construction of contramodel. So we now prove the normal implication instead of proving not this implies not that, which was the construction of contramodel. Like the inverse implication is that A does not have a proof, then A is not a tautology. So that was our proof by construction of contramodel, which we did for automatic theorem proving, and which we will do again in chapter 10 for predicate logic. Henking proof, and the Gödel and Henking proof is forward proof. And you use assume that all models of gamma models by inconsistency lemma. Gamma, if you add negation, is inconsistent. And now let M be a model of gamma. We construct, as a next step, witnessing expansion of the language, as we did. And we did the witnessing expression, and you do, and you do, and then you, that is, I repeated how you construct all this witnessing expression as a part of it. It's very nicely done, and and we know now that, okay, here is. So we have those witnessing constant. So for example, you have this, and then you have that A0 union dot A is inconsistent descent propositional logic. So that does not have propositional model. That means that V dot A is not true, and so VA of T is T for all V. So that sentence for those constructed formulas, you see, which we show how you construct those formulas, we form such a sentence when this is those BM and must be a propositional tautology. So that is first important fact. Now we replace this sentence by witnessing constants. So we add those new variables and you have still the sentence. This result is still a tautology, so it's probable in H. By monotonicity, in S, that whole sentence is probable. And now what we do, S0 is, by definition, S0 proves AI prime J, or all these pieces, you see, in S0, so you can apply modus ponens, and we get that S0 proves that formula. I want to have the formula. I want to have a proof of the formula A. So, and then I give you an example. So it's good to have an example. And now you eliminate those B's. Do you remember how we had the proof of completeness theorem from propositional? A was variables, and you had this crucial lemma, and you did exactly the same. Those elimination B1, B2, not B, not B1, etc. Look at this proof. It's exactly, or it's not exactly the proof, but that is the similar elimination. By elimination, finally, you get gamma proof A, and that is, so you constructed a proof of A. And of course, the proof for propositional logic, which I gave you, which was written 10 years or after the Henking, said, oh, that we can just adopt to propositional logic. So, and that's the proof we did, which is much easier to understand. And once you have that construction is exactly the same. And so we prove the Gödel theorems. A has a proof if and only if A is a tautology. Now, just deduction theorem is, you know what deduction theorem has A proofs in SB if the implication, and you have with gamma the same. And so in general, if gamma proof, we had in a system that proves in a system that we, and we do the same type. We're asking, can we do what we did in propositional logic? In predicate logic, you have, but we need to have a little bit, you have to be a little bit more careful with quantifiers. So, and so we generalize deduction theorem as follows. We now have, we construct the proof deduction of Bm from gamma with where Bi must depend upon the proof of the previous, and that are certain conditions which I don't want. And those conditions tells us how you can deal with a quantifiers. So, and when you have that, you can prove deduction theorem for predicate logic in really similar way as we did. So now we have deduction theorem that assume that we have some proof of gamma AB where no application of generalization rule to a formula that depends upon A has it as quantifying variable, a free variable in formula A. So you have that that special condition. So if you have proof of gamma from gamma A is proof of B under that condition, we can construct the proof from gamma A implies B. So deduction theorem has this special condition which depends on the way we use generalization rule. And deduction theorem now, when you want to do deduction theorem, it's a little bit, of course you do. I copied it from our deduction theorem. instead you have a formal proof. We do the formal strongest statement that gamma proves A implies BI, where BI is in the proof. And of course, and you do the base step, and you have modus ponens. You do by step-by-step decay. You have exactly the same proof for propositional connectives. You see, you can open slides on the book chapter, and you can see that you do exactly what we did. And now you have to consider that case, what happens that our BI, which is for all xbj. And that you have to apply those conditions, and we do it carefully. You see this, I wrote you carefully all those cases, and it shows that you can do also with that condition, you can finish the proof of the deduction theorem. So we have the deduction theorem, which is very important that we have it. And also we have different axiomatization. I just put you some of them, like Hilbert Ackermann. Hilbert Ackermann, they did the language they liked disjunction and negation. So the whole axioms were only with disjunction and negation. The whole quantifiers axiom when disjunction negation. That is modus ponens, because this is A implies B is logically equivalent in classical case. So that is Hilbert, and all rules, generalization, are rules rewritten with replacing implication by not A or B, and you have the Hilbert still, and then you and then if you want to have a good exercise, please take the Henkin proof for that system and go prove the deduction theorem. You can prove for that system. You will be able to do because it's complete. And now there is also what I said. Yeah, and I rewrote it in implication. So so there, and also the first of the and I gave you Elliot Mendelssohn book. So and here is Elliot Mendelssohn book. You see, these are our propositional axioms, which we use in our propositional part. And then you add two quantifiers axioms, and rule of inference, you have generalization, and Rashowa and Sikorsky, which have the set of formulas which are the most convenient to do algebraic proof. So these are Rashowa and Sikorsky. You have modus ponens, substitution rule. They use substitution, and quantifiers, introduction rules, and elimination rules. So you can see you can have different axiomatizations, because it depends a little bit also on technique you are using. You put up the axioms which are the most convenient for your axiomatization. And then I want to, we already discussed it in chapter 7, that Rashowa and Sikorsky generalize the completeness, which was only true and false to any Boolean algebra. So, and you have the that generalizes algebraic statement of completeness theorem to predicate logic. So now its derivable is valid. It means tautology in every realization. Realization in their language are the structure. Now you can do the structure in complete Boolean algebra, not only in TF, and valid in realization in the field of all subset of any space, valid in every semantic realization when corresponds to canonical structure, which here is the set of all terms of the language. And now you have, that's a beautiful, there exists non-general Boolean algebra, an infinite set that A is valid in every realization in J and A, and then you do the realization in Lindenberg-Tarski algebra, and that is predicate tautology. So the whole notion, it gives a very rich characterization of the notion of predicate tautology, and the proof is simpler than the one Henking proof, modern Henking, which I show, because it was invented later. So the whole way of putting things together becomes easier and easier. And so thank you very much. And you enjoy chapter 10, which is automated theorem proving in predicate classical logic, and constructive proof of completeness theorem, which is like, boom, you construct a model on the tree, still is the shortest proof you can have of completeness of predicate logic. Thank you.